For this problem here, we're comparing two cars that are traveling at 25 meters per second and are crashed into two different barrels. We want to think about the average force exerted on each car. So that to me indicates that we're going to be thinking about our impulse. So the first thing I'm going to do is I'm going to calculate our impulse using the mass and the change in velocity which were given for each car. So the mass is 1700, change in velocity is final minus initial, so 0 minus 25. And that gives me an impulse of negative 42,500 kilogram meters per second. The next thing I'm going to do is I'm going to use that impulse to go ahead and solve for the average force exerted on the car. So I'm going to do part A here, and I'm going to say that that impulse is equal to the average force multiplied by the time over which that force is exerted. And so I can say that negative 42,500 equals my average force times my time for the first part, which is 1.7, and I get that my average force here is going to be 25,000 newtons. Now, based on how I set it up, I technically would have gotten a negative here. Okay, I'm not actually going to worry about that though. It says just the average force, so we're just going to find the magnitude of the average force. But depending on how you set it up, it could absolutely be negative. When we round that to 2 sig figs, that's going to become 2.5 times 10 to the 4th newtons. Moving on to part B, I'm going to start once again with delta P equals the average force multiplied by my change in time. It's the same change in momentum because we have the same initial and final velocities and the same mass. The only thing that changes is my time is now 0.14 seconds instead of 1.7. And so when I go ahead and solve for this one, I get an average force of 303,570 newtons. Okay, and I'm going to round that to 2 sig figs, and so that's just going to become 3.0 times 10 to the 5th newtons. For this next one, we have an object moving to the right at a speed of 1.4 meters per second, and it experiences some force here that we see shown in this graph, and we want to know what its final speed is after that force ends. So the first thing I'm going to do is I'm going to calculate my impulse, and that's going to come from the area on this graph. And so I'm going to think about it being a rectangle, so base times height, which means my impulse is going to be 0.5, that's the base here of that rectangle, times my height, which is 2. And so I end up getting an impulse here of 1 kilogram meter per second. Now that I have that impulse, I can use that to get the velocity. So I'm once again going to think about my impulse, my change in momentum, but now I'm going to say that it's equal to mass times that change in velocity. So that impulse, which I know is 1, is going to be equal to 2.5 times v final, my final velocity, minus my initial velocity, 1.4, right? Any change, we always do final minus initial. And so I get that my new final velocity after that half a second force is applied is going to be 1.8 meters per second. So there's the answer to part A, 1.8 meters per second. And I was careful with my signs here. My force was going to the right, so it was positive. My velocity was also going to the right, and I made that positive. And since I got a positive answer then for my final velocity, it means that the object is still traveling to the right. And so that actually answers question B. For part C, I'm going to start once again with the impulse is equal to the area on the graph. We now have a new graph with a new force being exerted on the object, and we see that here. And so I'm going to find the area of that once again, the area under the curve. So that's going to be base times height, just like it was for the other part. But now my height is -2 instead of +2, so my change in momentum is -1 kilogram meter per second. I'm now going to take that impulse and use that to find my final velocity. So I'm going to say that impulse is mass times the change in velocity, so I know that impulse is -1. That's equal to 2.5 times the change in my velocity, so VF minus my initial velocity, which was 1.4. Now I realize this one was a little bit confusing because they weren't quite clear as to when this force happened. What they want you to do is think about this as going back to the beginning. So going back to when the object was traveling at 1.4, this is just a different situation where a different force is applied. And so when we do that, we solve for our final velocity, and we get that it's now equal to 1 meter per second. Rounding that to 2 sig figs, or making it be 2 sig figs, it would be 1.0 meters per second. And since it's still positive, even though our force and our impulse were ultimately negative, our final velocity was still positive, so it's still traveling to the right. For this problem, we have an 810-gram glider that collides with the spring at one end of the track. And we have two graphs here, one showing the force as a function of time, and the other showing the velocity of the glider also as a function of time. And so what we ultimately want to do is calculate this delta t, how long the glider was in contact with the spring. So the first thing I'm going to do is I'm actually going to start with my velocity versus time graph, and I'm going to calculate the change in momentum of the glider because I have enough information there. To do that, I know the mass of the glider is 810 grams, or 0.81 kilograms, and I know that my change in velocity, final minus initial, is going to be 3 minus -3. And so I find that my change in momentum here is going to be 4.86 kilogram meters per second. Now that I have that, I can use my force versus time graph to calculate that delta t there, using the fact that the change in momentum is the area under the curve on that graph. So that shape is a triangle, 1/2 base times height. So I end up with 4.86 equals 1/2 times my base, which is that delta t that I'm solving for, times my height, which is 36, that maximum force there. When I go ahead and solve for that, I get that my time here is going to be equal to 0.27 seconds. It's already rounded to 2 sig figs, so that's just my answer. So for this problem, we have a 60-gram tennis ball that collides with a wall and rebounds, traveling at the same speed, and we want to solve here for this maximum force that we see on the graph. So the first thing I'm going to do is I'm going to calculate my change in momentum using mass and change in velocity. So I know that my mass is 60 grams, or 0.06 kilograms, because we have to convert that. And my change in velocity, final minus initial, is going to be -36 minus 36. And the reason for that is I know that my ball is initially traveling at 36 in one direction. It then rebounds to travel at 36 in the opposite direction. So I need to indicate that change in direction with my signs. And so I end up getting a change in momentum here of 4.32 kilogram meters per second. Okay, I'm going to make that positive even though the answer comes out to be negative, simply because my force shown here is a positive force, and so that matches with the force shown. But the way I set it up, the answer would be negative. Now that I have that change in momentum, I know that that change in momentum is also equal to the area under the curve on this force versus time graph. So I'm going to go ahead and derive an expression for that area, and I'm going to break it up into 3 parts. The first is going to be that first triangle there. Its area is going to be 1/2 base times height. So 1/2 times my base, which is 2 milliseconds, or 0.002 seconds, times my height, which is that maximum force there. I'm just going to call that F. The second area I'm going to have is going to be that rectangle there, and so the area is just going to be base times height. My base is going to be 2 milliseconds for that as well, so 0.002 times my height, which is just that force. And then my third area is going to be that final triangle there, so 1/2 base times height once again. My base is 2 milliseconds, and my height is that force there. So when I combine all of those areas, I get a total area here of 0.004 times F. So that's going to be my total area, and that's going to be equal to my impulse. So I can say then that the 4.32 is equal to 0.004 F, and then I can solve for that force, and I find that the force ends up being 1,080 newtons. Once it rounded to 2 sig figs, so that would technically be 1,100 newtons if we were rounding it to 2 sig figs. For this problem, we have a small cart with a mass of 300 grams, or 0.3 kilograms, moving at a speed of 1.9 meters per second when it collides with a second cart with a mass of 5 kilograms that is initially at rest. After the collision, we know that the first cart, which has that mass of 300 grams, rebounds at a speed of 0.86 meters per second, and we want to know the final velocity of the 5 kilogram cart after the collision. So what I'm going to do is set up conservation of momentum. My initial momentum for my system must equal my final, and I'm going to call the 3 kilogram object 1 and the 5 kilogram object 2. So before the collision, the only thing moving is object 1, so m1 v1 initial is going to be my initial momentum. Afterwards, both objects are moving, and they're moving separately, so my final momentum is going to be m1 v1 final plus m2 v2 final. And I'm ultimately solving for that v2. So I can go ahead and plug in the things I know. I know the mass and initial velocity of cart 1. I know the mass of cart 1 still, of course, in its final velocity, making it negative because it rebounds. And then I'm solving for this V2F. So I go ahead and I solve for that, and I find that my V2 final is going to be 0.166 meters per second. That's already rounded to 3 sig figs, so that's just going to be my answer there. For this next one, we have a man standing on ice on a frictionless surface with a rifle. Him and the rifle have a mass of 70 kilograms. He's going to fire a bullet here, which has a mass of 10 kilograms. So initially, both objects are at rest. Afterwards, we know that the bullet is traveling at a speed of 500 meters per second, and we want to know the speed of the man and the rifle. They're going to recoil in the opposite direction, so we're trying to find that recoil speed. So to go ahead and solve this, I'm going to use conservation of momentum. So momentum initial equals momentum final. In this case, the initial momentum of our system is just 0 because neither object is moving. Afterwards, we have both objects moving, so I'm going to call the man object 1, and I'm going to call the bullet object 2, so we have the momentum of each one of those after the collision. We can go ahead and put in the things we know. We know the mass of the man. We're solving for the final velocity of the man and the rifle. The bullet, we know, has a mass of 10 grams or 0.01 kilograms, and its final velocity is 500 meters per second. So we go ahead and solve for the final velocity of the man, v1f, and we end up getting negative 0.0714 meters per second as our answer. Now the problem asks for the speed. Speed is the magnitude of the velocity. So we're just going to make that positive and round it to 2 sig figs, and we get 0.071 meters per second as our final answer, which makes sense because the man has significantly more mass than the bullet, so even though they have the same momentum after the collision, the man's going to be traveling much slower because of his increased mass. For this next one, we have a railroad car with a mass of 10,000 kilograms, moving at a speed of 6 meters per second. When a 6,000 gram load is dropped on it, so if it's dropped on it, it means the load initially was not moving, so it's going to be at rest. Afterwards, we have these two objects basically moving as a single object, and we want to solve for their final velocity. So we set up conservation momentum, pi equals pf. Initially, I'm going to call the railroad car 1 and the load 2. Initially, we just have the railroad car moving, so m1 v1 initial. Afterwards, they are combined, they're moving together, so I'm going to add their masses times their final velocity. So we're going to have 10,000 times 6 is equal to their combined mass, 16,000, times the final velocity, which is what we're solving for. And we end up getting that our final velocity is 3.75 meters per second. Next, we have a collision here between two balls of clay. The first one has a mass of 28 grams, is initially traveling east at a speed of 3.1 meters per second. The second one has a mass of 31 grams and is initially traveling north at a speed of 2.8 meters per second. We know that after they collide, the two balls of clay stick together, and they're traveling at some velocity that we're looking for, at some angle that we're also looking for. So this is when we're going to set up conservation of momentum in both the x and the y direction. So in the x direction, the only thing moving before the collision is object 1, which I'll say is the 28 gram ball of clay. So initially we have m1 v1, that's our initial momentum in the x, and then the two objects stick together, so it's going to be their combined mass times their final velocity in the x direction only, which would be this component. So we can go ahead and plug in the things we know. We could actually leave all these masses here in grams, But when in doubt, it's always best to convert to kilograms. You'll never go wrong there, so I will convert it to 0.028 kilograms. And then their combined mass, the 28 and the 31, give me 59 grams or 0.59 kilograms, times their final velocity in the x direction. When we solve for that final velocity in the x direction, we get an answer of 1.47 meters per second. We'll go ahead and do the same thing with our y momentum, so conservation of momentum in the y direction. And so what we end up having is just object 2 is moving in the y direction before the collision. We have the combined mass of both objects afterwards because they're moving together, times the final velocity, but only the y component of it, which would be that component there. So we go ahead and plug in the things we know. Once again, we are going to convert to kilograms, even though we don't necessarily have to here because there'd be grams on both sides and it would cancel out. And so we end up getting that our final y velocity is also 1.47 meters per second, which just happens to be a coincidence. So now that we have those two components, we're going to put them together in a triangle like we have here to be able to solve for the magnitude and direction of the final speed of the resulting blob of clay. And so to get that magnitude, we're going to use Pythagorean theorem, a squared plus b squared equals c squared. So both sides end up being 1.47. Like I said before, that's just a coincidence for this particular problem. But when we go ahead and solve for that final speed, we end up getting 2.08 meters per second. That's going to be that hypotenuse there. For the angle, we're going to say that tangent of theta equals the opposite side over the adjacent side. So tangent of this angle is 1.47 over 1.47, which you can take the inverse tangent of both sides, but you might remember that when the two sides are the same, the angle just ends up being 45 degrees. So there we have our angle. That's our answer to part A, 45 degrees north of east. And our velocity, if we're rounding to 2 sig figs, 2.08 just becomes 2.1 meters per second. So for this next problem, we have a coconut that is initially at rest, and a firecracker is going to explode it into 3 different pieces. One piece flies off west at a speed of 25 meters per second. One piece flies off south at a speed of 25 meters per second as well. And then we have this third piece, and we want to find the velocity and direction of its flight. And we're told here that these 2 pieces are half as much mass as this third piece. All right, so we'll call them m, m, and 2m. So we're going to want to set up conservation of momentum in both the x and y direction. I'm going to start with the x direction here. Initially, my momentum is 0. Afterwards, I have object 1, which I'll call that piece, moving to the left, so m1, v1, plus object 3 is moving at some speed in the x direction, m3, v3, x final, and that's just going to represent the x component of that third piece's velocity. We don't have to worry about object 2, which is the one moving south, because that's moving purely in the y direction. So we can go ahead and put in the things we know. We know that this is just a mass of m and a velocity of negative 25 because it's going to the left, plus 2m, and the x velocity of piece 3. So we go ahead and cancel out our m's, and we can solve for that final x velocity of piece 3, and we get that that velocity is going to be equal to 12.5 meters per second. Now that we have the x, we're going to go ahead and set up conservation of momentum in the y direction. So our initial y momentum is also 0. Afterwards, we have object 2 moving in the y direction, so m2, v2. Object 1 is moving purely in the x, so we don't have to worry about that. And then we also have object 3 moving in the y direction, or at least has a component of its velocity in the y direction, which would be that component right there. So we can go ahead and put in the things we know. The mass of 2 is just m times 25, negative 25 because it's moving south, plus 2m times the final y velocity of object 3. And we go ahead and cancel out the m's just like we did before, and we get the final y velocity of object 3 ends up being 12.5 meters per second as well, which is just a coincidence that happened to be the same as the x. So I'm going to take those two components now and put together my triangle and use that to solve for my overall velocity and the angle, okay, based off of the two components being 12.5 meters per second. So in order to get that overall velocity, I'm going to use Pythagorean theorem, a squared plus b squared equals c squared. So I have 12.5 squared plus 12.5 squared equals c squared. And I can solve for that hypotenuse, and I end up getting an answer here of 17.68 meters per second. And then I can also solve for that angle, and you may be able to see here that that angle is just going to be 45 degrees. Or you can set up tangent and say tangent is opposite over adjacent. So tangent of the angle is going to be equal to 12.5 over 12.5. If we go ahead and take the inverse tangent of both sides, we get that our angle here is going to be 45 degrees. So taking that velocity and rounding to 2 sig figs, we end up getting that it would be 18 meters per second at an angle of 45 degrees north of east. For this next problem, we have a package that starts at the top of a ramp, slides down the ramp, and undergoes a collision with another package that's at rest. In the first case, we want to think about the situation where the two packages stick together, and we want to solve for the velocity of the two packages when they stick together. The first thing I'm going to do, though, is I'm just going to analyze the motion of this object M as it slides down the ramp and figure out what its velocity is when it gets to the bottom of the ramp. And the way I'm going to do that is because this is not a collision. This is not a situation where momentum is conserved because gravity and outside force is acting on the box. So I'm actually going to use energy to go ahead and figure this out. So I'm going to say that my gravitational potential energy is going to be equal to my kinetic energy that I have at the bottom. So we can say mgh equals 1/2 mv squared. Okay, those masses, we don't know it, but it ends up canceling out anyway. And I can go ahead and solve for my velocity. So I'm going to say 9.8 times my height is equal to 1/2 v squared. And when I solve for my velocity, I get that my final velocity here is going to be equal to 7.67 meters per second. So now that I know the speed of that box at the bottom, I can go ahead and analyze the collision using conservation of momentum. Pi equals Pf. I'm going to go ahead then and say that box M that was sliding down the ramp is object 1 and the stationary box is object 2. So before the collision, just box 1 was moving, so we have M1, V1. Afterwards, we have both of them combined, so I'm going to add their masses times their final velocity Vf. I can go ahead and plug in the things I know. I know the mass of object 1 is just m, and its initial velocity was at 7.67. Afterwards, their combined mass is 3m times their final velocity. And so I go ahead and cancel out my m's and solve for that final velocity. And I get that the final velocity here is going to be equal to 2.56 meters per second. Rounded to 2 sig figs, it would just be 2.6 meters per second. So for the second part of this problem, I'm going to consider the case where the collision between the two objects is elastic, which means that they won't stick together. That initial collision was an inelastic collision when they did stick together. So the two objects will not stick together, and so that box will rebound back up the ramp, and we ultimately want to figure out how far it goes back up the ramp. Since it's an elastic collision, I'm going to set up both conservation of momentum and conservation of energy. So initially, only object 1 is moving, just like the inelastic case. But afterwards, they're moving, except they're going to be moving separately. So I'm going to say m1v1f plus m2v2f. I'm going to plug in the things I know. I know the mass is just m. I know that initial velocity is the 7.67. And that's going to be equal to m times the final velocity of object 1. I'm just going to call that v1 instead of v1f to not get cumbersome here with what I'm writing. And then 2m times v2f. I'm going to go ahead and cancel out the m's in each term. And then what I'm going to be left with is my one equation, which is just going to be 7.67 equals v1 plus 2v2. Energy-wise, when I set that up, before the collision, we had the kinetic energy of object 1. There was no work being done. It was elastic, so no energy was lost. And then after the collision, we're going to have the final kinetic energy of object 1 plus the final kinetic energy of object 2. So I'm going to have 1/2 m times the initial velocity of object 1, which was just 7.67 squared, and that's going to be equal to 1/2 mv1 squared, where v1 is the final velocity of object 1, plus 1/2 times 2m times v2 squared. I can do two things. I can cancel out the 1/2s that are in each term, and I can cancel out the m's that are in each term. And what I'm left with here is 7.67 squared is equal to v1 squared plus 2v2 squared. And there's my second equation. So from here, what I'm going to do is I'm going to go ahead and combine these two equations, and since I'm ultimately solving for v1, I'm actually going to solve this equation for v2 first and plug it in so I can get v1 as an answer. So if I solve for v2, it's going to be 7.67 minus v1 all over 2 is equal to v2, and then I'm going to plug that into this equation here. And what I end up getting is 7.67 squared equals v1 squared plus 2 times 7.67 minus v1 all over 2, that entire quantity squared. Now, I could go through and do some math here, and it actually isn't that bad, but what I'm going to do is I'm going to go ahead and use my calculator to solve this, which is perfectly acceptable at this point. And so I'm going to graph it. So the one thing I'm going to graph is this left side of the equation. So y1 is going to be equal to 7.67 squared. y2 is going to be equal to this right side of the equation. And I'm just going to substitute in x for v1. So it's going to be x squared plus 2 times this quantity 7.67 minus x all over 2 squared. Okay, and I'm going to look for the intersection. All right, using my calculator, second calc 5, I believe it is. And so once I get that intersection, I'm actually going to get two answers. My graph should look something like this. So there's 2 points where there's an intersection, and I find that x is either going to be equal to 7.67 meters per second, or x is going to be equal to negative 2.56 meters per second. Okay. I know that this should happen, right? I should get this number here, which happened to be my initial velocity for v1. That's what I was ultimately solving for. That is what we call the trivial solution. That would be if they never collided at all. So this is the solution I want. That's going to be the final velocity of object 1 after the collision. And it makes sense that it's negative because that indicates that it's going to rebound. So the last step that remains is to solve for that height. So I'm thinking about this object moving back at 2.56 meters per second. And I'm going to think about my energy in order to solve for that. Momentum is not going to be conserved as it slides back up, but energy will. So I'm starting with kinetic energy in this case, and I'm ending with gravitational potential, the opposite of when it slid down. So I'm going to have 1/2 mv squared equals mgh. The masses cancel here. I know my velocity is this 2.56 squared, and so that's going to be equal to 9.8 times my height. When I go ahead and solve for that, I get a height here of 0.33 meters, okay? But the answer actually asks for the height in centimeters, so if I convert that, it's just going to be 33 centimeters, and that's going to be the height that that object rebounds to. For this problem here, we have a new Olympic event where a person runs 100 meters starting from rest. They leap onto a bobsled here, and then they descend down a hill into a spring. And the goal is to compress the spring as much as possible. All right, and so we're going to think about two distinct periods of time here. The first is going to be our collision between our athlete here, Lisa, and the sled. And the second is going to be our trip down the hill here, okay, before compressing the spring. So the first thing we're going to do is analyze that collision, and we're going to do that using conservation of momentum. We'll call Lisa object 1, and the sled here object 2. So initially, just object 1 is moving within our system, and then afterwards the two objects stick together, and we can solve for that final velocity. So plug in some numbers that we know here. The mass of Lisa is 40, her initial velocity is 12, that's her maximum speed in that dash. And that's going to be equal to the combined mass of Lisa and the sled, 40 plus 20, or 60 kilograms, times their final velocity. And so when we solve for the final velocity, we get an answer of 8 meters per second. For the second part, that trip down the hill, we're going to analyze that using energy. So E initial plus our work being done equals E final. We're starting with kinetic energy. Now we're thinking about Lisa and the sled moving together. They also have gravitational potential energy because they're up at some height. There's no work being done because it's ice, and we're going to assume that it's frictionless here. And so we're going to end with spring potential energy. So I can substitute the formulas for all those energy types, and I gave myself a little more space here to enter all the numbers that I know. I know the mass of the two objects is 60. That's their combined mass times their initial velocity at the top of the hill, plus 60 times 9.8 times the height, which I don't actually know. However, I do know that the hill is 50 meters long, and it's sloped at an angle of 20 degrees, so I can use that to solve for this height here. So that height is just going to be 50 times sine of 20, or 17.1 meters. So I can substitute that in. And that's going to be equal to 1/2 times the spring constant, which is 2,000 times x squared. I can go ahead and solve for that x, the distance the spring is compressed, and I get an answer here of 3.46 meters, which when we round to 2 sig figs, just gives me an answer of 3.5 meters.